We're going to look at some quantum numbers in this video, and really our goal by the end is just to know that there are 4 quantum numbers and kind of how to come up with them and perhaps the shapes that correspond. This lesson really goes with the next lesson as well. Putting those two pieces together will sort of give you the whole picture. So don't be too concerned if you're a little confused after only seeing half the picture in this video. So the Heisenberg uncertainty principle states that you cannot know the location and velocity of an electron exactly at a certain point in time. And so this idea takes us to the new idea for the appearance and possible location of electrons. So we don't know exactly where they are. They're in shells. Maybe they're not. Where are they? We can't find them. So we're going to talk more about that. So Schrödinger built on this idea and created an idea to express the possible location of these electrons by using quantum numbers as the guiding principle. There are 4 quantum numbers that describe the location and spin of an electron. So let's talk about the first principal number, n, and we've kind of seen n before. So Bohr actually was kind of the originator of this n idea. So his idea that atoms contain shells for the electrons to exist in, and that's what n's talking about. It's talking about sort of the number of shells that an atom has. So the number of shells in an atom gives us our first quantum number. So and this is going to these numbers tie into the period number as well. So if something's in period 3, it's going to have an n value of 3. If it's in period 7, it'll have an n value of 7. So the principal quantum number n is the quantum number that describes the size and energy of an atomic orbital. Let's talk more about n here. So the quantum number will correspond with the period the atom is in on the periodic table. I think I said that already. And so here's a possibility of something all the way up to existing in period 7. The spaces between these shells are not the same. You can see like we've got a bigger space here than we do here. And as the number of electrons increases, some will spend less time near the nucleus. So they're just going to generally be less affected. So electrons up here aren't going to feel the pull of the nucleus quite as strongly. So it was discovered that tied to the quantum number n was the shape of the orbitals. These shapes became known as subshells, and subshells have specific shapes. So what this is also saying is that electrons, they can only exist sort of on these flat lines here. They don't exist in between, say on this portion of the line. They don't exist in there. So they're either here or they're found up here, and this kind of moving around, when they get excited up to an higher state, they gain more energy and they drop back down. That's when these light wave particles get emitted. So the subshells make it so electrons only have specific locations they can occupy, like I just said. It's basically like it's going up a staircase. So you're either on the stair or you're not on the stair. If it were a ramp, you could kind of be anywhere on the ramp. Like you could find your location. I'm here, I'm here, I'm here. But when it comes to our staircase, we're on a stair and there's no in between. So that is n. Let's talk about the next one, L. And L depends directly on n. So this is our second quantum number, and it describes the shape of the orbital. So n tells us how many orbitals there are, and L tells us the shapes, and there's different shapes. So to determine the number L, this is supposed to be a fancy L, and orbital shapes are possible. You just need to take whatever the highest number for n is and subtract 1, and then kind of repeat this step. So L is equal to, I guess it's like a little equation, if you will, n minus 1. So if n equals 1, you take your equation, you plug in 1, and you find you get 0. And this 0 actually tells you the specific shape of the orbital that electron will exist in. And so when you have an L shape of 0, you get what we've got here as circles. So we have a circular one. So this 1 represents like your first shell. So your first shell has this small circle. Then when you get up to your second shell, notice that the circle is bigger. If you put it over top, it would cover it up like that. And when you get up to the third one, it's a bigger one, and if you put that over top your first diagram, it would just get bigger and bigger and bigger. And this, I guess, it kind of, at this point, looks like the Bohr-Rutherford diagrams that we've drawn in the past. And that's true, but not quite true. So anyway, bottom line is that these are known as spherical, or the S shape. Notice I also had the S's here. And they are round. So L equals 0, you get some round shapes. Well, what if you get n equaling 2? Well, this time you subtract and you get an L value of 1. Now what this L value tells you is that there are 3 possible outcomes. So I call these balloon-shaped ones, and so you might find an electron flying around in here. Now notice all we've done from the first picture to the second picture is we've turned it. And so again, you might have an electron there, or maybe you have a couple electrons, and then you could turn it one more time and you get another electron, another electron. So these are known as the p-shaped orbitals. They don't look like a p, but they are the p-shaped orbitals. Well, what if n equals 3? Well, this time you actually get 5 different corresponding values. So your electron will appear somewhere in, again, I called it balloon shape, so we have 5 different outcomes. You can see them, and they've got some crazy names. And these are the d-shaped orbitals. Again, notice there's a d in front of each of these. And the last option we can have here, so far as chemistry and the periodic table allows us, is for n equaling 4. We get an L value of 3, and this time we have 7 outcomes. I don't know what to call these ones, but we get 7 different outcomes, and these are known as the F-shaped orbitals. So if you have an atom with a lot of electrons, then those electrons can be found anywhere in the orbitals. So if you got a simple one, it's probably just got a circular one. But if you've got something with 100 electrons in it, you're probably going to have like all of these shells existing all on top of each other. And somewhere in those F-shaped ones, you're going to have the electrons flying around. So moving on to the next quantum number, this one's called m sub L. This number describes the orientation of the orbital. Whole numbers like -1 or 0 or 1 are used to describe it. This ties directly back to the shapes that we just saw on our previous slides. So if you're talking about an L value of 1, then you're referring to the p orbitals, and thus you have 3 outcomes or possible shapes of the orbitals. So here's an example. So let's say you're doing your calculation, and for this one, I guess L would equal 1. So you actually have 3 possible outcomes for when L equals 1, because it's actually more like, well, we've got a -1 here. That's one of the options, because again, we talked about there being 3 orbitals, and I'm just kind of arbitrarily saying that this is the -1. It may not be. And then this is the 0 one. And then we've got here is our third orientation. So again, when you got an L value of 1, that means you can have 3 different options here. So the way this works is your answer would be it would be +1, 0, or 1. So you have 3 different shapes that that could occur for your electron to be found within. This is basically every answer to everything. So what it says here is, and we sort of did this one earlier, we said that if you have an n value of 1, and then of course this is n minus 1, this category here, the L, you get an answer of 0. And when you have zeros, you have S-shaped things. You're only going to have that one S shape, which means you only have 1 orbital. When you get up to 2, again, you can always have the previous orbitals, so we still can have an L value of 0. We still have that first round spherical orbital, and again, whenever you have an S value, your ML value is 0. Again, you only have 1 option. So it doesn't get interesting until we get up to here. So we've got n minus 1, 2 minus 1 is 1, and that means when L values are 1, we're talking about the P's. In fact, if you look down this chart here, every time we have a 1, it corresponds with a P. And previous to that, every time we had a 0, it corresponded with an S. Notice that? And even in looking down here, 0 and S, 0 and S. And whenever you have an S, notice you have a value of ML of 0. It repeats itself all the way along here. So when we're talking about this p orbital, and we just looked at it on the last slide, we have 3 possible orientations of those shells. One of them is a -1, one's a 0, one's a 1. I'm not going to specifically tell which is which. I'm just going to say those are the options. And there were 3 pictures we drew, right? Or there were 3 pictures. Looking down here, again, we have another p orbital. Again, we have the same 3 values. Again, we have 3 orbits. And even down here to our next, the 4p, again, we have the same 3 numbers. Again, we have the same 3. It doesn't change until we get down to the d orbitals. And remember, when I showed you the d orbitals, there were 5 pictures. That's why there are 5 of these quantum numbers. And when I showed you the f orbitals in the very last slide, right here, there were 7 pictures, and that's why there's 7 numbers. Count them all up. So you could assign each one of these numbers to each of those 7 pictures. So somewhere in there, you're finding an electron. So the questions are going to be like calculate these numbers, and really every answer is already done. It's on here. You just kind of have to sort of find it. Now there's one other thing to sort of differentiate, because there's a we're going to see here the Pauling principle in a second says that no two quantum numbers can be the same. Well, you can have 2 electrons per shell. That's something we're going to learn next lesson here. So what this number does is it identifies the spin of something, and there's always 2 possible numbers for this, only ever. And again, I've kind of arbitrarily assigned this. So if you're spinning in the counterclockwise or clockwise, whatever you want to call this, you could say it's spinning in the plus direction, and then the opposite would be it's spinning in the negative direction. And so these numbers are just going to help us figure out which way an electron's spinning in an orbital. So here's what I just alluded to, the Pauli exclusion principle. And it says that in a given atom, no 2 electrons can have the same set of quantum numbers. So really what that means is, if you look at helium, and helium has 2 electrons to put, it's going to be in the 1s circular, when we're talking about s, we're talking about circular, and it's got 2 electrons. So, it's got 1 electron here and 1 electron here. It's got 2 electrons in this shell. And what this principle is telling us is that for us to differentiate between these 2 electrons, that this one arbitrarily has a spin of plus a half, and this one has a spin of minus a half. And that is the only difference between these 2 electrons. This will allow us to put 2 electrons in every shell. Again, that's something we're going to focus more on in the next section. So a couple of questions here we'll look at. So if we want to solve for the quantum numbers, if n equals 1, you substitute 1 in and you get 0, and that tells you that your ml is 0. That tells you it's a circular or spherical shape to it, and that you may have only 1 electron in there. You might have 2, so one spins one way, one spins the other, hence the plus minus.